In this lesson, we're going to look at optimization. So optimization is an application of differential calculus, and usually we want to find out how to make something the largest or the smallest, or figure out if our revenue is the most we can make or the least we can make, something like that. But there are always limitations when we try to find the maximum or the minimum, and we want to find those constraints. So these are word problems, so you should be reading these questions very carefully, and if you need to draw a picture, then you should probably do that. You can look over these different steps, but I'm just going to go through an example right away and apply these steps. So for example 1, two positive numbers have a sum of 60. What is the maximum product of one number times the square of the second number? Now we're looking for the maximum product. This is going to be our optimization equation. And this first sentence just gives us some extra information. So for this first sentence, let's actually write this out algebraically. So two positive numbers have a sum of 60. We don't know if they're the same, so we can call the first one x and the second one y. And if we add them together, that should be 60. This is our optimization function, this next one here, because it's saying find the maximum product. Well, how do we usually find product? Product of a square is usually length times width. In this case, we know that one number times the square of the second. So let's say x is our first number, and then y is our second number. So this is x is our first, and then y can be the second one. So that would be x, and then multiplied by the square of the second times y squared. This is our optimization function. The thing is, we don't really want to differentiate this with terms of x and y inside there, but we do have enough information to do this all in terms of x or all in terms of y. I'm just going to do everything in terms of y. It really doesn't matter what you choose. So I'm going to replace our x then with 60 minus y. So that now I only have one variable. Then I'm going to simplify this. So this is our final optimization equation. The next step is I'm going to differentiate this so I can find the maximum. So we need to find the critical points. I am differentiating this in terms of y. So this will be 120y minus 3y squared. My third step is I'm going to set this to 0 to find my critical points. And then I'm going to factor to do that. So factor out of 3y. So it looks like that our critical points are y equals 40 and 0. Now it wouldn't make sense for y to be 0 because it has to be a positive number. This needs to be positive. In my fourth step, I'm going to confirm that y equals 40 is a maximum. So I'm going to do my number line and plug it into product prime, or p prime, to see if my original product is increasing or decreasing. So if I plug in, let's say, 1 into p prime, I'm going to get a positive number. That'll be 120 minus 3. Now if I plug in a number like 50, we will get a negative number. So that's increasing and then decreasing. We have confirmed that y equals 40 is a max. So we're going to state that. So there's a max at y equals 40 since f prime changes from positive to negative. if y is 40, we do need to find the x. And that's going to be 60 minus our y, which is 40. So x is going to be 20. Now I'm going to state my final answer because we want the maximum product. Maximum product is P equals x times y squared. X we found was 20, y we found was 40. This altogether is 32,000. That's our maximum product. Let's do another example. In this next example, we want to have 40 feet of fence to enclose a rectangular garden along the side of a lake. We want to find the maximum area that we can enclose. Now, if we take a look at this picture here, we are given a rectangular garden. We want to maximize the area, but we also have enough information to create something about a perimeter here, because it's saying there are 40 feet of fence to enclose this rectangular garden. Now, how do we usually calculate our perimeter? We would need to first define our variables. So let's say x is our width and y is our length. Then our perimeter would be 2x plus y. Remember, we don't have a fence along the lake. So this information here is 2x plus y. Our perimeter is equal to 40. Now looking at our optimization function, we want to maximize area. So the area of a rectangle is x times y, length times width. And again, we don't want to have two variables when we want to find the derivative of the area. So we're going to change this all in terms of x or all in terms of y. I think this time it doesn't really matter though. I'm going to turn everything into all in terms of x. So I'm going to rearrange this equation here so that we can replace our y with 40 minus 2x. And then I'm going to simplify this a bit further. All right, so this is our optimization function. Now we'll take the derivative of that to find its critical points to find the maximum. So that's 40 minus 4x. Then we're going to set this to 0 to find its critical points. I'm going to factor out 4. So x is equal to 10 in this case. Now we're going to create a sign diagram with x equals 10 as our critical point. We're going to plug in numbers on either side of 10 into a prime to figure out if it's positive or negative, and this will give us information about the area to see if it's increasing and decreasing. So let's pick a number on the left side of 10. Let's say 1. That's 40 minus 4, which is positive. Now if I pick 20, we're going to get a negative number here. So that confirms that our area will be increasing and then decreasing. So 10 is a maximum. And we can find our y value by plugging it into 40 minus 2x. And we know that x is 10. So this is 20. And we know a max is there since a prime changes from positive to negative. Finally, we can say the maximum area is 10 times 20, or x times y, which is 200, And we're given the units of feet, so this will be feet squared, and that's our final answer. Let's try another example. We have an open top box, and it's made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending up the sides. How large should the squares be to make the box hold as much as possible? So we are trying to optimize the size of those squares so that the box can hold as much as possible. If you want a box to hold as much as possible, we're talking about the volume of this box. Now, usually volume of a box would be length times width times height. Again, we don't want three variables, so we are going to have to figure out how we're going to create this so we only have one variable to consider. Now let's look at the side picture. We know that this box has to be 20 by 25 inches. And we know that these congruent squares have a side length of x. So this is your square here, and they're congruent squares of length x. That means if it's a square, your length and width are x and x. And this occurs for every square that happens in the corner here. Now, if I think about the actual length along here then, along here, this is going to be 20 minus the two x's on either side. And then on the bottom here, similar, but it's going to be 25 minus the 2x. So the length of 25 minus the 2x on either side. So now we can actually replace length within height with 25 minus 2x multiplied by 20 minus 2x multiplied by x. Because we have our length, width, and x is our height. Now we want to simplify this. So if you multiply this through, this is 500x minus 90x squared plus 4x cubed. So that is the function we're trying to optimize. Trying to optimize a volume. Second step is to take the derivative of this, which will be 500 minus 180x plus 12x squared. Our third step is to set v dash to 0 because we want to find the critical values. And we can graph this out instead of using the quadratic formula. And if you use your graphing calculator and find its intercepts, you can find that x is about 3.681. So to do this, you're going to use graphing calculator and find the x-intercepts. Our next step is to use that critical point and create a sign diagram. We want to know when v prime is positive and negative so that we can confirm when our volume is at its maximum. So if we plug in a value, let's say 1, which is the left side of 3.681, into v prime, that's 500 minus 180 plus 12. This is a positive number. Now if you throw in a really large number, let's say 100, into v prime, we're definitely going to get a negative number here. So we can confirm that our volume is increasing and then decreasing. So we do have a max at 3.681. And we know this because the prime changes from positive to negative here. Now we want to state our final answer. The question was asking how large should the squares be. This was our x value, so our square should be 3.681 by 3.681. And the unit given to us was in inches in the original question, so our final answer needs to be in inches as well. Now I want you to try example 4, but I'll get you started before I let you do it. We are trying to maximize an area of the rectangle. That means you need to find the area for the rectangle and represent it in terms of x and y, because the semicircle equation was given to us. Now, I need you to take a look at the picture and decide how we're going to determine length of width of our rectangle. So we can say that y is our y values, so that could be our y, it's our width, and our length can be x and x, because we're looking at the distance from 0 to -3 and 0 to 3. Or something like that. So we know that those two parts of our length need to be equal to each other. So go ahead and try to figure that out, and when you're ready, press play. Okay, so your first step is to determine your optimization function. So area is length times width. We said that length can be 2x and our width can be y. So you change to 2xy for your area. We know what y is. It's given to us in the original question. You replace y with the root of 25 minus x squared. Then you're going to take the derivative, and it is a mess to take this derivative, but we can use our graphing calculator to find that x value. So once you find the derivative, you can plug it into your calculator and then use it to find your x-intercepts. This will be a critical point. Then the next step, we're going to create the sign diagram for a prime to see when it's positive and negative. And you should get that the maximum is at 3.536. That's because a prime changes from positive to negative here. And then lastly, we find the length and width. So we said that the length is 2x. We know that x value now, so you just plug the 3.536 in, and your final answer for length should be 7.071. For width, we know that's y. We're going to plug it into the original equation with that semicircle. So that's the root of 25 minus 3.536 squared, which is 3.535. We're going to do one more example together. In a swim and run biathlon, Jill must get to a point on the other side of a 50-meter wide river, 100 meters downstream from her starting point. She can swim at a rate of 2 meters per second and run at a rate of 5 meters per second. Toward what point on the opposite side of the river should Jill swim in order to minimize her total time? So we are given some rates here. Swim at a rate of 2 meters per second, run at a rate of 2 meters per second. These two pieces of information are very important because this will give us the velocity of her swim time and run time. So the swim would be distance over time for the velocity of the swim. And if I want to change this around, we know that time is then going to be distance over her velocity for slipping. Because we want to minimize this. Now we don't want things in D and S and T, so we're going to take a look at this picture and see how we're going to represent this. We know that Jill must get to a point on the other side of a 50-meter wide river. So the river is 50 meters wide. We're going to draw that into our picture. That's the width of the river. We also know 100 meters downstream from her starting point. So this is her starting point here, and this is going to be 100 meters downstream from her starting point. So this whole length here then is 100 because that's downstream. We don't know how far downstream that she should go. So we can call that x. If I call this x, that means this length will be 100 minus x, because this would be 100, the total length of this downstream, minus how far she should swim to the opposite side of the river. Now, how would I find our length here from point A to point B? This would be using Pythagoras, which is the square root of x squared plus 50 squared. Now we want to relate this in terms of minimizing her time. So we need to rewrite t d over s. Our distance is going to be from our start to point P. So that's the root of x squared plus 50 squared is 2,500. And s, our speed is given to us, the rate is 2 meters per second. Plus how far she needs to go downstream, the distance here, over her running time, 5. So we need, this is talking about her swim time, this is talking about her run time. Second part, we need to take the derivative of this, which is lengthy. So I'm just going to go ahead and take this derivative, but you would need to use your chain rule to do this for the first part here. And then for this one, this is just 100 divided by 5 is just a number, so that's going to be 0. And then negative x over 5 is just going to be negative 1 over 5. Looks like a mess, but you're going to put this in your calculator and see when this whole thing is equal to 0. So a graph t prime in graphing calculator. And find the x-intercept. So if you do that, you should get x is about 21.822. Now we want to create that sign diagram to show that this is going to be a minimum at 21.822. So you want to find the sign for t prime. You can plug in values such as 1 into t prime. Again, you can use your calculator to do that. You should get a negative number, which means that t is decreasing here. And then on the other side, you can pick a number, say 30, plug it into t prime. You should get a positive number. Again, remember to use your calculator for something like that. So this will confirm that we have a minimum at x equals 21.822. And that's because t prime changes from negative to positive here. Now the question is, at what point on the opposite side of the river should Jill swim? This is our x value. We want to know at what point, so that's the distance from kind of the component of her start to the final point. So final sentence, she should swim 21.822 meters because that was the unit given to us in the original question, downstream. stream. For the other examples, I want you to try these on your own, and I'll leave the solutions there for you to check your work after.